So let us start our day with any homework questions you had. Okay, is there anything from the homework assignment? You did 4-6. Am I showing my screen? Do you see the screen? Yes, okay. 4-6. Thanks, Jack. Ooh, that is not written very well. Okay, 47. Let's just start attacking your question. Someone asked for 47. Oh, this one was interesting. Oh, Libby, same one. Okay, that's funny. Two of you asked for it. Okay. As we do 47, we are going to be reminded of our, wow, I can't write neatly today. We're going to be reminded of something that we learned. We got a couple of shortcuts out of the lesson. Got a couple of shortcuts. One was, oh, and here's the question. What power should be right there? Oh, Jack, you got it. Molly, you got it. Okay, so let's think of what this is saying. Isn't this saying that 4 to some power is being multiplied by 4 to the third power, and you end up with 4 to the 11th power? Now, do you remember what we learned? Oh, close. You're very close, Maddie, with a Y. And Lexi and Will. Oh, actually, no, you're right. You're right. Sorry. I'm looking at the wrong thing. The 9s are wrong. Sorry. At first I said the 9s were wrong, right, but it's the 8s. The 8s, all of you that said 8. It's an 8. Look at me not doing my math well in my mind. 4 to what power times 4 to 3 more powers is, how many must there be if then you multiply it by 3 more and you end up with 11 4s all multiplied together? Does that make sense? 4 times 4 times 4, and we're talking 4 to the 11th, so how many must there be here? If you got 3, 4, 5, 6, 7, 8, 9, 10, 11, 1, 2, 3, 4, 5, 6, 7, 8. Shouldn't there be 8 4s being multiplied by each other? And then 3 more, and that makes 11? Does that make sense? So what was our cool shortcut that we learned in our last lesson? It's that if you have the same base thing, we were doing x's and y's and variables, but it's true with numbers too. 4 to the 8th power and 4 to the 3rd power is really 8 plus 3, 11 4s, all being multiplied together. So our cool shortcut was, if you're multiplying and the bases, let me remind you that the bases are the big number in an exponent setup. If you're multiplying and the bases are alike, like the 4 and the 4, you can just add the exponents, and it's more simple to say 4 to the 11th than to say 4 to the 8th times 4 to the 3rd. But there are a couple things that we said were very important. First, you had to be multiplying, right? You had to be, this 4 to the 8th had to be being multiplied by 4 to the 3rd for us to be able to use 8 plus 3 and get 4 to the 11th. And that's because powers are little multiplication problems, right? 4 times 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 4. And then if you multiply by another little multiplication problem, what you actually have is just 11 4s all being multiplied. But this has to be multiplied. It can't have a plus sign, or else this whole trick doesn't work. Okay, let's look at another. Did you not have to do 49? No one asked about 49. Let's just do, oh, you had to do all of them. Yeah, okay, let's do 48. Let's do all of these. This really makes us think about what we learned in our shortcuts. And the question is, what power must be on the top so that when you divide out t to the second, you still end up with 14 t's being multiplied. Lexi, you're right. What was our shortcut with dividing? Okay, this will help, I think. If you were dividing and the bases were the same, we subtracted the exponents. So it would be something minus 2 is 14. So a couple of you have done 14 minus 2. But that's not what this is, right? This top thing minus the bottom thing got you 14. So try again. What's the top number? Uh-huh. Good, Peyton. Oh, good, Jack. I'm sorry, Morgan. That's Morgan. Sorry. That's hard. Okay, Molly, yes, you got it. Okay, if I haven't said your name, it's because you sent me the wrong thing. I'll tell you this, it's not 12. It's not 24. Our shortcut was this power minus, oops, that's supposed to be a highlight, minus this power equals that power. So think about it opposite. It must be 14 plus 2 would get you this, right? There you go, Allie. Good, 16. Okay, so why did the shortcut of subtracting work with dividing like bases? Because that's our shortcut. We learned if you're dividing with like bases or the same bases, remember the base is the big part, in this case t's, then you can subtract the top minus the bottom. Subtract the powers and you get the final actual power that's on it. So let's not use this exact example. If you'll let me not use such huge numbers, let's just pretend like it was t to the 6th over t to the 2nd. Let's do it the long way. Didn't we learn 2 lessons ago that you can just write it out the long way? That's 6 t's, 1, 2, 3, 4, 5, 6 t's divided by t times t. Those are supposed to be t's. They're getting kind of crazy, looking like 7s. And didn't we say that anything in the numerator and the denominator cancels to 1? Remember when we were canceling variables and numbers? So what ends up left on the top? It looks like an F, yeah. T to the 4. So so what was the shortcut? We said, well, if it's the top number, 6, and it cancels with as many as there are in the bottom, does that make sense? Then it's going to always be subtraction. Because whatever you have in the top, let's say you have 6 of them, but if you've got 2 of the same thing in the bottom, a pair, a 2, 2 and another 2 are going to cancel, which takes 2 away from 6, which leaves us with 4, which is the more simple way. T to the 4th is much simpler than saying t to the 6th divided by t to the 2nd. So these were, I'm sorry, my t's looked like F's and 7s, but do you remember the 2 shortcuts now? If you're dividing things with the like bases, you can subtract their powers. If you're multiplying like bases, you can add their powers. Yeah, let's keep going. So that was what, 48? Let's do 49. 13 to the 5th over 13. Oh, this is a good one. 13 to the what equals 1. Ha, 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 ha. Anybody know what should go in the yellow? Lexi, good thinking. You're on, I know what you're thinking. You're on the right track. Jack, you're right. If you said 0, you're on a right track, but the power shouldn't be 0 down here. Okay, let's do a quick review. Libby, actually, this is something we talked about right before you came. Morgan, that's right. Okay, quick review of something. x to what power equals 1? 0. This is our interesting lesson we learned. Oh, good, there's Maddie. Yeah, you weren't here, Libby, when we learned this. It's right before you came. 1,000 to what power equals 0? I'm sorry, equals 1. 1. Yes. So our lesson that we learned right before you came, Libby, is that anything to the 0 power has an answer of 1. Anything to the 0 power. 0 power, power 0, answer is 1. I don't care if I put star to the power of 0. You say the answer is 1. Hey, thank you, Allie, for that. Okay, let me put Maddie down on our attendance. Hey, Maddie. How are you? We're just reviewing our homework and our concepts from the homework. Okay, so if the way to get an answer of 1 is that the left side should be to a power of 0, does that make, what 5, and if our shortcut is that we subtract, no prob. Sorry, Maddie. How are you going to get the left-hand side's power to be 0? 5 minus what is 0? There you go, Libby. Okay, some of you have said 4, but 5 minus 4 isn't 0. Good, Allie. 5 minus 5 is the power of 0. Tricky, right? So you had to remember a couple of things. You had to first think, how in the world do you get an answer of 1 out of a power? So you had to at least have this hidden in your head, that anytime something's taken to the power of 0, the answer is 1. Then you had to think on the left, well then how do I get a power of 0? If we're dividing, you use subtraction, so you just had to think, okay, 13 to the 5th over 13, it's going to have to be to the 5th also. That would give you 13 to the power of 0, right? 5 minus 5 is 0, which equals 1. Now, I got another way maybe you could have thought about it. Let's say you didn't remember any of this. What's always 1? What over what? Gotcha, Jack. I'm not answering this question very well, but what if you have 10? 10 over what is always 1? Good, Libby. 10. Good, Allie. What if I had x? X over what would be 1? X, exactly. Good, Lexi, Maddie, and Allie. So there's another way you could have thought of this, is anything over its exact self always cancels to 1. Yeah, I should have put anything over anything, shouldn't I have? If there's a thing in the top of a fraction and the thing in the bottom of the fraction, they always cancel to 1. In fact, that's what we were talking about right here. We've been using that for a couple of lessons now. Something in the numerator, something in the denominator cancels to 1. Something else cancels to 1. So, do you now see, and this is why I couldn't tell you this, the day I taught you this lesson, I hadn't taught you this subtracting the powers concept. But here's the connection, right? If anything over itself equals 1, isn't that always going to be the same as subtracting 5 minus 5, one of these situations? X to the 4th over x to the 4th. If we use our shortcut, 4 minus 4 equals 0, that's the same as x to the 0, which equals 1. See the connection here? But you could have told me back here that, well, if something is over its exact self, that cancels to 1. Cool connection, right? In fact, I told you to just memorize this 4 lessons ago. Thanks, Jack. Now I am actually giving you the reason why. The reason why anything to the power of 0 is 1 is what it basically is indicating is that the original problem had the thing over its exact self. So when you subtracted the exponents, you got a power of 0, which is the thing over itself is a 1, meaning the power of 0 creates a 1 as the answer. Crazy, right? Any power of 0 means the thing has canceled itself out on the top and the bottom of a fraction. I love it when people say, oh, thank you, Allie. It's so cool. Does anyone else find that kind of cool to figure that out? Let me show you again. I want to get some more oohs and ahs. Okay, so, I don't know. Let's see, 6 to the 4th over 6 to the 4th. Oh, thanks. Y'all are cracking me up. Livy, Lexi, Maddie, you're making me so happy. Right, so if you didn't even know the power rules, wouldn't you be able to probably think through, okay, 6 to the 4th, whatever number that is, even if you had to figure out the number, 6 times 6 times 6 times 6, wouldn't you know that you're going to get the same thing on the bottom? 6 times 6 times 6 times 6, that thing and this thing would cancel each other out to 1, right? But now, in the new world of the shortcut, you would think, okay, well, I've also been taught that if I'm dividing and the bases, the big number is the same, then I can just subtract these powers, 4 minus 4, and my answer would be 6 to the 0. Doesn't that mean that this answer and this answer are the same as each other? Cool, right? Thanks, Maddie, for being like, ooh and ah, and everyone that's going ooh and ah. So basically, this is where we get the rule that I taught you 4 lessons ago. Anything to the power of 0 is a 1. So do you see now why it's anything? Anything to the power of 0 is 1 because it means that the anything over itself had a power, it subtracted the powers, you got a power of 0, it made it a 1, it canceled itself. Crazy, right? I love it when math comes together. Y'all are just really making me so happy with all your oohs and ahs. Okay, anything, so let's jump back into your homework though. Let's keep talking about that. How do you feel? Any more homework questions? Those were the good ones. They made us think real hard. What about earlier? What about earlier in your homework? Did you have to do any evens? Maybe I'll give you some evens. Oh, you did 4 through 11. That's all. Yeah, you did. You did all of it. Good. I'm glad you think so. Okay, 65. 65 must be a review-y kind of thing. Okay, so 65 is not the new stuff. There's always at the end of your section, there's stuff that you're supposed to already know. And this one is in the prerequisite skills, so this is something you already know that's going to be useful coming up again. Okay, so if we have 65, the question is y over 50. And then it says evaluate if, and it tells you y is -5. It tells you that in the directions. So you're going to need to write this with a -5 over a 50. And then how do you simplify this fraction? That's all you need to do. Negative over a positive, the overall answer is negative. Okay, so 5 over 50, treat this just like we did a couple of lessons ago. If you can't figure out how to reduce it some way that you've been taught in the past, the way I taught you is to prime factor the thing. Remember? 5 is prime, so it's just 5 times 1, so the only factor is really 5. Prime factorization of 50 is 10 times 5, so you do your factor tree. 5 is prime, 10 isn't. Break it down. So 50 is 2 times 5 times 5. And we said it's overall a negative answer. Now you cancel any top and bottom stuff to 1. And then what do you actually have left? Only a 1 in the top 2 times 5 in the bottom, a 10, and the overall sign of the answer is negative, because a negative over a positive is a negative answer. Division rule. Does that make sense? So for some of you, you reduced fractions. Instead of doing the prime factorization, you probably just thought in your head, what goes into 5 and 50? You said it was 5, so in your head you divide by 5 and get 1, divide by 5 and get 10. Negative 1 over positive 10 is negative 1/10. Either way you do it's fine with me. That help? Let me pick something from your homework else. Okay, 21. How did you do it this one? 2y times 9y to the 4th. Okay, there's 2 potential tricky things on this. You want to try to chat me what you think the right answer is? How do you multiply these together and get a simpler answer? Okay, so someone who just sent me something, you fell for the trick on the numbers. Oh, you fixed it. Excellent. Okay, someone else fell for the trick on the Jack, multiply your numbers together and then you'll be there. Someone else fell for the trick on the power of y. So everyone think, if there's no power written, what's the power that's there? Let's just review that. That's it, Jack. That's it, Libby. That's it, Morgan. Good, Molly and Maddie, for answering my specific, and Maddie, yes, for answering my specific question. Exactly. Tricky, right? Okay, so if you're going to use our shortcuts, good, Allie, that's the right answer. If you're going to use the shortcut of adding the exponents, there's one place where you could get tripped up. You've got to remember that if a variable doesn't have an exponent, there's still one of it, right? I think I told you this the other day, but I'll repeat it. I have students in Algebra 1 that still go, when they're doing a problem like that, they go along and, let me see, Maddie, did you give me a final answer? Oh, yes, Maddie, that's right. I see it up there. Maddie with an I. Perfect. Okay, so I have students that in Algebra 1, if they're multiplying stuff with variables, they still put little powers of 1 on any variable that doesn't have a power on it, just so they don't mess that up. Because if you're going to follow the add the exponent rule, you've got to remember that that's 1y and 4 more y's, a total of 5 y's. Oh, you know what? I don't know. Jack, it's funny you would say that. I haven't taught this in Algebra 1 yet. We teach it later in the year. Funny. So you're covering exponent rules before they do. Okay. Now, okay, so that's the right power on the y. Does everyone see that? A y times 4 more y's being multiplied. It's 5 y's overall being multiplied, but the error that we tend to make once we start using our shortcut is that we forget that a 2 times a 9 is just the same old multiplying that you've done in the past. So at least one of you was tempted to put an 11 here. But it's not, right? It's 18. But do you see how you could, if you're thinking add, then you go to the numbers 2 and 9, which are just regular numbers in a multiplication problem, and you're tempted to add them. Be careful. They are regular numbers. Multiply them. The whole adding thing is a little shortcut. It's a shortcut to use with exponents only. It's not to use with big numbers in multiplication. So this is the kind of thing that I've seen trick people, and that's why I wanted to see how you feel about it. What if, let me just see something else. I'll just make one up. Negative 4x to the third times negative 3x. What's the simpler way to write that? final simplified form. It's all multiplication, right? That's what those parentheses mean. Good, Lexi, and good, Libby. Exactly. Only use the adding shortcut with powers, not with the big numbers. Good, Morgan, that's right. Yes, Maddie, good, good, good. Oh, y'all are going to be so good on your quiz. Anybody else want to shoot me an answer here? Allie, I think Allie, I think your numbers are just mixed, but yes, I believe you have the right answer there. Okay. Think about your signs. Okay, 2 people have sent me that the final answer is negative. Is that really correct? Isn't a negative thing times another negative thing a positive thing? Right? The rules are for multiplying or dividing, same signs, positive answer. So we don't want a negative on that answer, we want a positive. Now, if you sent me a 12, you were right. 4 times 3 is 12. X to the good Jack, you've got it. Someone is still being tricked by this power on this X that's invisible. Yeah. What should the power really, if this is X to the third and this is another X, good Molly, there's a power of 4 here because there's an invisible 1 there. Realize if you put X to the third, it's like you have completely left off this X that's multiplied in. We can't ignore him just because he only has a power of 1 that's not written, you know? Does this make sense? Negative 4 times negative 3 gets you the positive 12, and then look at your variables. X to the third, X to the first, X to the fourth. How do you feel about that? Okay, let me give you another question that's going to be, I'm looking now at your quiz. I'm thinking, how do I review you for your quiz? So watch what I do. One of your quiz problems says standardized test practice. It's number 5. And it says basically simplify this particular fraction, and then it gives you A, B, C, or D. So those are good because you get to pick from 4, but don't let it fool you. Okay, so what if it was this? 6x over x to the 4th. Oh, God, no problem. 6x over x to the 4th. What's the final fraction? So what you want to text me or chat me is the top slash the bottom of your fraction. What's left on the top once you cancel? What's left on the bottom? Good, Maddie with an I, exactly. I'm assuming there's a fraction bar after the 6, right? Yeah. What's left on the top? What's left in the denominator? There's not a 5 in the answer. Yeah, okay. Maddie with an I, you're exactly right. Oh, did I already say that? Yes, that's the exact right way to chat it to me. Perfect. Yeah. Interesting. Okay, I've gotten a lot of answers, none right, some close. Okay, let's not make this harder than it is. Didn't we say if there's something on the top and the bottom that are the same, they could be canceled, right? So on the top you have a 6, which you could break into a 2 times 3, but I think you and I both know there's no number down here to cancel with it. 6 is not going to cancel. There's not a 2, there's not a 3, there's not a 6 in the denominator. 6 isn't going anywhere, but the x on top, does it cancel with one of the x's on bottom? Look at me writing that out the long way. See what happens there? That x and one of these x's cancel to 1, so more simply, 6 over x to the third, or chat it this way, 6/x caret 3. Yes, Lexia Morgan, you sent me that. Good, good, good. So I think what I think some of you used, did someone give me a 5? I think you tried to use adding the exponents. Did you send me that, Allie? Yeah. I was talking for a second and I missed some. Yes, you did, Allie. Perfect. You sent it way, like, at the very top. I think you were first. You and Maddie were at the top. Good jobbers. But so you've got a couple of strategies. When you look at something like this, you can think, okay, anything in the numerator that's the same in the denominator, I can cancel. So break the top thing and the bottom thing down. Cancel. See what's left. And that's kind of how I handled reducing this as well. You can reduce fractions that way. Break down the 5, it doesn't break down, he's prime. Break down the 50, 255, cancel, cancel. What's left? You end up with -1/10. That's always a strategy. Or if it had been something like, let's say it had been this, 6x to the fourth over 2x to the second. You could have thought, okay, reduce the 6 over 2, divide both of those by 2, but use my subtracting rule for this, x to the fourth over x to the second. 4 minus 2 is 2. So 3 and then x to the second. But in your mind, be logical. Doesn't this mean there were 4 x's up top, only 2 down in the bottom, and therefore 2 of them canceled? So where are those 2 x's? They're in the numerator, and there's nothing left in the denominator but a 1, and hopefully we all know that you don't have to put over 1. That's not simple. So the shortcut is good here. If the shortcut, I'm going to teach this today, but the shortcut here would have been a 1 minus 4, which would have given you a -3 exponent. I'm going to teach you about negative exponents today. But all that would have meant is that your x, where is your x to the third? It's down here. The reason you got a negative is because all the leftover x's were in the denominator. Why do you get a positive answer here? 4 minus 2 gives you a +2 because your leftover x's were up here in the numerator. Do you follow that? Because it's where we're about to go. Yes, yes, no. Okay. Let's just go there. Perfect jumping off point. Okay, why is it that if we follow the shortcut, x to the fourth over x to the third, shortcut is subtract the exponents, right? 4 minus 3. Do you agree that the simpler way to write that is x to the first power, or even not even a first power? You don't even need the first power, right? But let's think about why we got a +1 as our answer. Because if you did this the long way, let's do it the long way. X times x times x times x, writing the prime factorization out on top and on bottom. You cancel, pair, cancel a pair, cancel a pair, and you end up with the x on the top in the numerator, right? That is why 4 minus 3 gave us a +1, because the bigger number, 4, was in the numerator, and so it kind of wins, and the extra x that's left is up top. But today we're going to figure out what we do if it was set up this way. What if it was this problem? And we used our shortcut. Wouldn't our shortcut still say, okay, you can do 3 minus 5, but do you agree that 3 minus 5 is -2? What did that mean? That we get that for the answer, basically. Do you see why that would be what you would write if you were following the shortcut? because the rule is subtract the powers, whatever you get. Does that make sense? The -2, which is what you get, 3 minus 5, that goes on the x. But now let's do it the prime factorization way and see why did we get a -2? Does anyone know why we got a negative this time? Because where are all the leftover x's once you cancel? See where they all are? Cancel. Cancel. They're in the bottom, right, Jack? They're in the denominator. So we would normally have written this answer, forgive me for having to scoot up, oops, 1 over x to the second. But when we follow the shortcut, subtract the powers way, we get x to the -2 power. Here's the big bombshell lesson of the day, folks. These are the same thing. Does that make sense? Depending on how you do it, you're going to get 2 different answers, but the answers are both right, which means the cool thing of the day to learn today is a negative exponent just means that actually all the leftovers were on the other side of the fraction. So if you subtract 3 minus 5 and you get x equals -2, which would mean write x to the power of, not x equals -2, you get -2 and you put x to the power of -2, what that really means is x to the second power should be in the denominator. So here's the interesting connection. Here's how I look at it. Once I understand it, I almost have a funny, shortcutty way of looking at it in my head. If I ever see a negative exponent, I say to myself, ooh, he really wants to cross the fraction bar. He wants to go across. He's in the numerator. He wants to go into the denominator so that he can be his positive self. Does that make sense? Funny, right? But it is always the way it works. If you get a negative exponent when you're doing this, it really means Mr. X to the -2 would like to be, he's more his positive self if he's in the denominator. See how when he's in the denominator he doesn't have a negative power? It's just +2? Because he's in his right place. His leftover, the 2 extra x's were in the denominator. That's where he belongs. But when we did the shortcut always leaves you in the numerator. So x to the -2 standing alone, isn't it really in a numerator? So if he goes down in the denominator, he gets to be his positive self. Interesting. So let's do some more of these. Let me even flip to the, we are doing 4-7 now, folks. We are in the new lesson. Oh, how funny. Their very first example was actually the one I just did, and I didn't mean to even do it that way. Okay, so let's not do their examples. Let's just keep playing around with this. Okay, so Allie, good question. Allie says, what's the simplest form? Generally in math, if you're not told, writing where the positive power, where it's going to have a positive power is best. Generally in math. But sometimes you're told, rewrite this in its negative power, or rewrite this. If they tell you to rewrite it with its negative power, then you would rewrite it that way. But what does that mean? So let's say you have 1 over x to the -4th. I'm not even going to tell you where it came from. I'm just telling you that's, you got here, 1 over x to the -4th. What did my cutesy little rule, what does it say? It says whenever you see a negative exponent, he wants to cross the bar. A negative exponent, he will be more comfortable if he can cross the fraction bar to become his positive power self. positive version of himself. Which means if this x to the negative fourth is in the denominator, where does he want to go to be his positive self? Up, up, up into the numerator. Then he gets to be his positive power self. Do you see what I did there? Based on what I showed you on the last page, anytime you have something in a fraction with a negative exponent, it wants to go to the other part of the fraction. If it's in the denominator, take it up into the numerator, like I did here. That is my dog. Someone's probably walking in our yard. She's flipping out. I'm so sorry. I won't be able to stop her until they leave. Sorry. It's funny when she'll walk in here and like bark at me like, do you hear what I'm trying to say to you? You need to come check this out. But I don't. Okay, do you see what I did here? This is kind of the thing, maybe this is something you want to write down. When you see a negative exponent, it wants to cross the fraction bar, whether that means go up into the numerator from the denominator or down, like the first one. And then it can be a positive power. So someone wrote to me leaving the 4, I'm not going to say who, but you know who you are. You left the 4 somewhere else. But the 4 is the exponent on the x. So see, when I say he wants to go up, I mean all of him. X to the negative fourth wants to come up in the top of the fraction to become his positive power self. Does that make sense? Let me show you another one. So it just depends on where it all begins. If I had a to the negative third, where is he? Just sitting there like that. Is he in the numerator or the denominator? He's in the numerator. Good, Lexi. Any number that doesn't look like it's in a fraction is actually in one. It's just in the numerator. You don't have to write over 1. So if I say, okay, a to the negative third, could you please write him where he will have a positive exponent? Where does he really want to be? Down in the denominator, which means how do we need to write that? We're going to have to put a 1 to hold the numerator and then a to the positive 3 power. So, and the 1 is up here because that's the only way to show that we have a to the third in the denominator. You know what I'm saying? Let's keep doing it. So this is your rule. If you see a negative exponent, he wants to cross the fraction bar so he can be positive. You take the whole thing, a to the negative fourth was in the denominator, comes up to the numerator. A to the negative 3 was in the numerator. He wants to go down to the denominator. Now he's a to the positive 3. You see what I do? So I do 2 things. I make him cross the fraction bar, and then I change his exponent to positive. What if I asked you something weird and I said, could you write this where he'll have a negative exponent? Well, what's going to force him to have a negative exponent? Crossing him back across the fraction bar. See what I did? He's happily down in the denominator with his positive 3 exponent, or his positive 3 power. But if the direction said, write him where he has a negative exponent, well, that's him going up into the numerator. So I kind of think about this fraction bar as having this magical quality where if you take something with a power across it, it changes the sign on that power back and forth. It has the power to change the sign on your exponent. If b to the third power was positive down here in the denominator, if you bring him up in the numerator, oh, now he has to have a negative. It's a portal. Good, Allie, I like it. It's a portal. The fraction bar is a portal, and what the portal does is it changes the sign on the exponent. Gotcha, Molly. And it works with numbers. If I had, so example 1a, yes, they're the positive and negative exponent parallel universes. Example 1a has 6 to the negative second, and it says, write an expression using a positive exponent. So what does that mean? If 6 to the negative 2 is sitting here like this, it must be in the what? Numerator or the denominator right now. It must be in the numerator, right? So to write it with its positive exponent, he needs to go into the denominator. Then he gets to be positive. But how do we show, what do we put here to hold that numerator spot? Good, Lexi. Good, Morgan. You've already sent it to me. Good, Allie. Yes, a 1. Does that make sense? So it's, there's a little bit of a thing we have to point out. When a number is just sitting here with no denominator, there is an invisible over 1, right? But we don't have to write it. But if the number is in the denominator, you have to put a 1 to show that the numerator even exists. That's the only way to show that the 6 to the second power is in the denominator. You can't just write this. That doesn't make any sense. And you sure can't just write it, oh, look, I put it low. Well, no one knows that you put that in the denominator. You have to actually write 1 over. Does that make sense? So, double standard. You don't have to write 1s if they're in the denominator, but you do have to write them to hold the numerator, to show that the numerator is there. So the next thing example 1b says is write this with a positive exponent. Gotcha, Molly? So where does, you want to try to chat me what that should look like? Why don't you try to chat me? Use the fraction bar. Good, Morgan. Good, Allie. So what would be a top? What would be on bottom? Remember, for a power, use the little caret. Good, Lexi. We are, yes, the new lesson is the negative exponents. We kind of just moved into it a minute ago. So remember, Mr. x to the negative 5th, if we want to write him where he has his positive exponent, he needs to cross the fraction bar. Right now he's sitting, okay, here's your rule. If you've got something with a negative exponent on it, if you just take it across the fraction bar, whether that means up into the numerator, because it's already down, or whether it means down, it changes its power to be the positive. So if x to the negative 5th, the directions say write it where it's got a positive power. Are you back, Libby? Then you got to ask yourself, okay, well, it's in the numerator right now. Do you agree with that, Molly? Does that make sense? That an x to the negative 5th just sitting there must be a numerator, because otherwise it would have, 1 over x to the negative 5th. Does that make sense? So anything that doesn't look like it's in a fraction is in the top of a fraction with an invisible over 1. Okay, so since we've determined that Mr. x to the negative 5th is in the numerator, or the top of a fraction, the place where he will get to have a positive exponent is if he will cross the fraction bar. So what's crossing the fraction bar? In his case, down to the denominator. Now he gets to have a positive exponent of 5. But when we make it into a fraction like this, we've got to indicate somehow that there is a top of this fraction. And if there's nothing there, then there's actually a 1 there. And there's no simplifying it, really. Not this one. There will be some that we could simplify at some point. I want to do this is not in your book, but I just want to show you something. What if you had x to the negative 3rd and y to the negative fourth. And I said, rewrite this where everybody has their positive exponent. Any ideas? Don't they both need to go across the fraction bar to become positive? Yes, Jack. It is two different variables, so they're not going to cancel with each other. Exactly, Lexi. So I'm not saying cancel these because they don't cancel. X and Y don't cancel with each other. I'm not saying use any cute shortcuts on the powers. We're not doing that. It's not X over X. I'm saying just rewrite them where they get to have their positive exponents. Well, doesn't that mean that Mr. Y to the negative fourth needs to come up into the numerator? Yeah, good, Molly. Good, Allie. Yeah, you got it. And doesn't that mean that this guy, x to the negative third, wants to come down into the denominator? So in a case like this, they just switched places because they both had their negative exponents, so they wanted to cross the bar. So they like crossed the portal, met each other along the way. Remember, if it helps you like it does me, the fraction bar is just like this magic thing that when you cross it, it makes the sign, it changes the sign on the exponent. Making y to the negative fourth come up from the denominator into the numerator made it have a positive on its exponent. Taking x to the negative 3 that was in the numerator down into the denominator gave it a positive exponent. Yes, all you have to do is move it up or down and it changes it back to a positive exponent. So what if I said, oh, let's see if I can, what if it was this? X to the third, y to the negative fifth. And I said make everybody have a positive exponent. Do you see that only one needs to move? See, x to the third is already in a good place to have a positive exponent. He's up in the numerator. But who's not got a positive exponent? Mr. y to the negative fifth. So he wants to come up. So in the end, this would be an x to the third and a y to the fifth, all in the numerator. You see what I did there? So if the directions are, please write this where the exponent is positive. If something's already sitting in the fraction where they have a positive exponent, they stay there. You only have to make people cross the magical fraction bar if you want to change the sign on their exponent. Crazy, right? Okay. Let's look at example 2 now. Using this concept, it's crazy talk, exactly. Using this concept of negative exponents. They give you this, and here's the thing about this homework is you've really got to read the directions. Make sure, if they say write it where it's got a positive exponent, you do what we just did. These directions say write 1/9 as an expression using a negative exponent. This is very interesting. Because I don't see any exponents here. And so when they give you a problem like they do in example 2 in your homework, they will have actually given you a number that could be broken down to something to a power. Do you see the number that is something to a power of 2? It's a perfect square. It's the number 9. So which number can you change to something to a power? The 9. 9 is 3 times 3, which is 3 squared. See what I did there? So look for the number, when they ask you something like this in the homework, look for the number that could be broken down into something times itself. 9, if you do a factor tree, it's really obvious. It's 3 times 3, which is 3 squared. Okay, now that you've turned the 9 into a number with a power, it's actually asking me, write it where it's negative. Well, if 3 to the second power is positive in the denominator, where will he be negative? If I pull him up into the numerator, right? Exactly, Allie. He's 3 to the negative 2 if I put him up in the numerator. Now the 1 would just be times 3 to the negative 2. So do I need to write the 1? Not anymore. 1 times 3 to the negative 2, I don't need to write that. Do I need to write the over 1? No, don't need to write that either. So you can turn 1 over 9 into something with a negative exponent, but you've got to figure out what number can break down into something to a power, and then you've got to move it to where it will be negative, which is in the numerator because it started out positive in the denominator. It's a crazy kind of question, I know. They basically want to see if you can move things around and manipulate them. So some of these may not be, I guess, let me give you another example that's in the teacher's book. You may not automatically know what the power or what to change 125 into that has a power, but if the directions are this, rewrite this as an expression using negative exponents, you can bet that the number that they gave you can break down into something with a power. So how are you going to do that? Factor tree, maybe. If you don't know it, factor tree it. I think of 125 as 5 times 25, 5 quarters. I think $1.25 is 5 quarters. 5 times 25. So the 5 is prime, 25 keeps going. 25 is 5 times 5 times 5, which could be written 5 to the third, right? So 1 over 125 could be written as 1 over 5 to the third. That's the same as the number 125. And since the direction said write it where it has a negative exponent, where does he need to go? Up into the numerator. Then he'll have a negative exponent. 1 times 5 to the negative third, you don't have to write that 1. You don't have to write the over 1. This is a good answer for what they asked you to do. What if they asked you to go the other direction? Imagine this. What if they asked you to go the other way? What if they said, here's 4 to the negative 2 power. Could you rewrite this all the way out to its fraction with positive powers? So where is 4 to the negative 2 right now in a fraction? Isn't he in a numerator? Good, Lexi. If he's in a numerator, to be his positive self, we'd need to write him in the denominator. But then if it says write it all the way to its simplest, form, 4 to the second power is actually the number, what? 4 times 4 is, what's 4 times 4, folks? 16. Good. Good, Allie. Good, Lexi. The thing I think is so interesting here is whatever you start with and end with, these are actually the same. They basically mean the same thing, but look how different they look. Look at that. 4 to the negative 2 is actually the same as 1 over 16, but look how different they look. But they really mean the same thing. So as this homework may get you good at moving back and forth, the goal really is, do you understand that these are the same as each other? And do you remember our big lesson today, which is crossing that fraction bar changes the exponent's sign. If you cross it from the numerator to the denominator, 4 to the negative 2 becomes 4 to the positive 2. And if you had to change it back to negative, you'd go back into the numerator. Okie dokie. Let's do some powers of 10 stuff. That's what example 3 has us work on. Okay, example 3 has us working with this teensy-weensy little hydrogen atom that's this big, 0.00. Man, how many zeros was that? 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 1. Okay. It's this much of a centimeter across. Tiny. It wants you to rewrite this as a power of 10. Okay, let's take what we did a little while ago. We did talk about powers of 10. Remember what we said about powers of 10? How like 1 with 4 zeros is 10 to the 4th. 10,000 is 10 to the 4th. Or like a 1 with 2 zeros is 10 to the 2nd. Let's see if we can figure out what happens on the teensy side of the decimal. Let's take this down. If a 10 is 10 to the 1st power, right? 1 0 power of 1. And we know a 1 is 10 to the, help me out here, anything to the power of what is 1? Good, Lexi. Good, Jack. 0. Then what if I move one spot to the right? Do you see how I've been moving the 1 over? In fact, just to keep it, let's just put all of them. Okay, so we had 1,000 was 10 to the 3rd. 10,000, 4 zeros is 10 to the 4th. So what happens when we start going into the decimals? Instead of 1, we go to the 10th place. So 0.1. Isn't that 1/10? Hang with me here. If I bring that up to the numerator, isn't it 10 to the -1 power? You see how I used two things we know and I wrote that? One thing we know is a 10 or anything has a power of 1 on it. It's just not written. And if I'm going to pull it up into the numerator, then that means 10 to the 1. Now I crossed the fraction bar, right? So I changed it to 10 to the -1 power because now it's went from the denominator to the numerator. What about 0.01? That's 1/100th. That's how you would say it. 1/100th is 1 times 10, 1 over 10 to the 2nd power, right? We know that from up here. 100 is the same as 10 to the 2nd power. And if I write it in the numerator, it changes it to a negative power. Let's do a few more of these and see if we can figure out the same kind of cool shortcut that we figured out with the larger powers of 10, which are this. The power of the 4 is just how many, if you've got a 1, how many zeros are after it? Or basically, if you've got a number up front, how many places are after it? That's where the 4 comes from. Does that same thing work if they're after the decimal place? Well, maybe we can just look at what we figured out so far. Is this -1 how many zeros are between the decimal and the 1? Nope. It's actually how far the 0 or the 1 is away from the decimal. When we start going to the right, a -1 means we're only one space, we've only got one place after the decimal. A -2 means we only have 2 places after the decimal. Do you know why? Because if you think about your place values, you know how this is the ones, and this is the tens, and this is the hundreds. Have you ever thought about how you don't have another oneths? Have you ever thought about that? You don't go to the other side of the decimal place and have a oneths and a tenths and a hundredths. Nope, you go straight to tenths. and then there's the hundredths. So you don't have that extra little, I know once would be very hard to say. So you have this little padding on the left where your power on tens is, if you look at where the first place is, then you count how many places are after it. That's the power on the 10. But when you're on the right side of the decimal place, it's purely how many digits are there after the decimal. So look down here on the bottom left. 1 digit after the decimal, then you're in the 10 to the negative 1's place. 2 digits after the decimal, you're in the 10 to the negative 2's place. What is 10 to the negative 1? 1/10. It's the tenths. What is 10 to the negative 2? It's 1 over 10 to the positive 2, which is 1 over 100, which is the hundredths. Interesting connections, right? So this page is really helpful if you want to screenshot this. It helps us see that if we're given something like this and we're supposed to write it as a power of 10, which is what the directions actually said, write it as a power of 10, that's 10 to the, since it's on the right-hand side, it's a negative exponent, right? Because it's really one, it's the THs, you know, that's the one, I don't know what this is going to be, the 100 millionths or 10 millionths, but it's in the THs. It's in the 1 over power of 10 world, which means negative exponent, if we're going to write it in the numerator. And then to figure out which negative exponent, you see where your decimal is and just figure out how many places are being used to the right. 1, 2, 3, 4, 5, 6, 7, 8. 8 places, power of negative 8. Good. You screenshotted it? Yeah, cool. That makes sense? So when we're working with powers of 10 to the left of the decimal, so on the what we think of as whole number side, you look at the first number and you count how many digits are after it to the decimal. That's the positive exponent on the 10. 1, 2, 3, 4 things after the first one. But on the right-hand side, you just count how many total digits after the decimal. 1, 2, 3, 4, 5, 6, 7, 8. And since it's in the decimals, it's in the negative exponent land. With this page, I think you could take anything that they give you in the homework. Here's another one. So they say that 1/10 of a nanometer, I don't know what they're talking about, but it has 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So they give you this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then a 1. And they say write that as a power of 10. Well, because we're in, so these are two things you got to think about. Because we're in the teeny tiny decimals, we're in the negative exponents for 10. Because we're on the right-hand side of the decimals, we count how many total digits are showing up after the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's your exponent. Does that make sense? Negative of it. Good, Morgan. Good, Lexi. Cool? Okay, that's a couple of those, and you've got your pretty page, and if you didn't screenshot it and you need to come back and watch, or here you go. Here it is again, if you find this helpful. Maybe you want to go back and write it in your own words. Last thing the homework asks you to do, and then we're going to get out of here, is in example 4, they want you to go back and use the stuff we did earlier with the negative exponents, but they're going to give you one of those situations where you have to plug in a number for a variable. So the problem says n to the negative 3, but then immediately says n equals 2. And then when it they say evaluate, I believe. What do the directions say? Yeah, the directions say evaluate. Evaluate. Okay, anytime it says evaluate, you know you're going to be able to get to a number answer. And here's what I want you to think. just get that number where it has a positive exponent and all the way multiply it out. Like if it's, you know, a number that you can take to the power, go ahead and multiply out the power. Because it's the simplest way to look at a number. Do you agree that when you look back up at this, this is the more straightforward way, 1 over 125 and 1 over 16, and this is kind of the weirdo way of thinking about it? So once you get to the ones where they say evaluate, your goal is going to be get it where the exponent's positive, and then if the number is taken to a power, multiply it together. Because numbers can be multiplied out, not variables, but they're not leaving this a variable, are they? They're telling you put 2 in here. So now let's rewrite it, 2 to the power of negative 3. Okay, this is very hard to think about until we get it into its positive place. If 2 to the negative 3 is sitting here, it must be in the numerator or denominator. Where is 2 to the negative 3? If it doesn't look like it's in a fraction, then yes, Jack, it's actually in, good Maddie with an I, good Allie, it's actually in the denominator, the numerator, sorry. Oh, goodness. So it's in the numerator, which means for it to become positive, it wants to go down into the denominator, right? So look what I did. I took it, I pulled it down, and then it gets to have a positive power of 3. So first get it to where it has its positive exponent on these problems, and then go ahead and multiply out the power on the number, because it's not a variable to the third, which we couldn't work. It's 2 to the third. So careful on this. 2 to the third is not 6, is it? 1 over what? What's 2 to the third? Good Maddie with an I, good Lexi. Who else has told me already? Yes, Maddie with an I. Yes, yes. 2 to the third is not 6. That's 2 times 3. 2 to the third, good Jack, is 2 times 2 times 2. Good Morgan. What's 2 times 2 times 2? It's not 5. 2 to the third is not 2 plus 3, and it is not 2 times 3. Good Allie, good Maddie with a Y. It's 2 times 2 times 2. Remember, 3 times you multiply the 2. Don't let that last thing fool you. Think about what an exponent means. It doesn't mean 2 times 3. It doesn't mean 2 plus 3. It means 2 times 2 times 2. 3 times itself. This is your final answer. You want to do one more? This is another one like example 4. We'll call it example 4B. It's just in my book though. Evaluate r to the negative second if r equals negative 4. So again, directions say evaluate. So what I want you to think is, okay, let's make it the pretty answer. Let's get it into its positive exponent spot, wherever it needs to go, up or down in the fraction. And I'm going to go ahead and multiply out, like do the power to the number. Because when it says evaluate, it's never leaving variables in the problem. It's always going to tell you what the variables equal. So that means we know that negative 4 belongs right here, right? So we've got negative 4 being taken to the power of 2, negative 2. First, let's get him where his exponent is positive. Right now, he's in a numerator. If we bring him down into the denominator, he gets to have a positive power. Do you see how this could be a little tricky? This negative 4 is still a negative 4. See? What changes when you bring him from the numerator to the denominator is that his power gets to become positive, but not the negative 4 itself. Don't let that fool you. The negative 4 is still a negative 4. Now work out what is negative 4 times itself. Isn't that what the power of 2 means? So Maddie with an I, you were right. Allie, you were right. First time, I think. Yes, Allie, first time you were right. Lexi, that's right. Careful of your sign rules. Isn't negative 4 to the second power actually negative 4 times itself? That's, Maddie and Will, exactly what should be in the denominator, right? If good, Jack. Good, Allie, yes. Isn't negative 4 squared negative 4 times itself? Good, Morgan. Negative times negative is positive. 4 times 4 is 16. That's your answer. Does that make sense? You see how we got there? So let your process on these be plug in the number that they tell you first, carefully. Then move it, if it's got a negative exponent, which goodness, they probably all will, move it, if it needs to go to the denominator, move it down, change its power to be a positive, or if it needs to come up, move it up and give it a positive power. Then do the exponent, do the power math. If it's a negative times itself, that's a positive 16. Okay, that is everything. That's all the different things you'll have to do in your homework. Don't forget that your quiz is due tomorrow, if you could get it to me by tomorrow morning. Okay, so a couple things. I do want to say one more thing about the quiz. There is one problem where it says compare centimeters. Centimeters are what part of a meter? Do you remember when we did a problem or two like that in our homework? It has to all be in the same unit. So don't set up, if it says, remember the one where it was like 88 feet is what part of a mile? That's the one we did. You wouldn't say 88 over 1 and reduce that fraction. You have to get miles in feet. So we put 88 over whatever it was, like 2,000, blah, 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 and reduced it. Thank you, Lexi. 5280. 5280. Same thing with the one problem like this you see on your quiz. You've got to put everything into the fraction as the same unit. So if it's centimeters to meters, you need to change meters to centimeters, and it's handed to you. So if you just think that way, I think you'll be fine. And the first couple are like our 2 lessons ago, where you just do the prime factorization of the top and the bottom, cancel, 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 write what's left. Okie dokie. 10 questions, 10 points each. Do your best. If you can get it to me before tomorrow morning at 11, I will grade it tomorrow. Otherwise, get it to me by Sunday night. And do your homework by Tuesday. Have a great weekend. Bye.